Jody exists. So what we're doing here is adding resistors in series and parallel. Now your normal circuits could be consisted of resistors, capacitors, inductors, transistors, all sorts of little things, right? But we're just for now sticking with resistors. So think of light bulbs attached to wires, okay? Now when we do this, we have Ohm's law to govern this, which is V equals IR. A voltage is equivalent to a current multiplied by some resistance. And the weird thing about this equation is there's only one R in it, which means that if I have a setup where there's the positive, negative terminal ends of our battery, if I have a setup with lots of resistors, and let's just say like this is R1, R2, R3, R4, you get the idea. What is that value right there? What am I looking at? Well, what we can do is we can kind of look at this in a few ways, and there is a way we can look at it later on where we can look at individual voltage drops across one resistor. But what we're going to do now is we are going to just take this entire circuit as a whole, and let's try to figure out what the equivalent resistance or the total resistance of this entire circuit is. Now, because this circuit is in series right now, we can tell that because there's only one path to go around here, and when we go through all these resistors, I have to go through them all in one direction in one positional space. We actually add all of these resistors up to find the equivalent resistance very easily. We simply just sum each of the resistors. So if we have some number of resistors, let's just call them N, and we'll go from I to N with them. We'll just sum up all the resistors. So in our example here, it would be like R1 plus R2 plus R3 plus R4 plus R5. That's it. You literally just take everything that's in series and add it up for resistors, okay? Now, this is a little bit different than what you'll have to do if your resistors are in parallel. So let's say we've got another circuit here, but these are in parallel branches. And let's just say that there's like more down here, right? Like there's more of these parallel, however many more. In the end, they'll all come back together and come back up. So how do we deal with this? Well, when we're adding things in parallel, the equivalent resistance or the total resistance in parallel is calculated a little bit strangely. What's actually going to happen here in parallel is as we add more resistors, the equivalent resistance in the circuit actually is going to go down. And the reason why is, think about it this way. If we think about it, we're in Pittsburgh near the tunnels. If you have more tunnels open or more roads open, you can kind of spread the cars out more. You're never going to get a traffic jam. Everything can pass through easily. So even though you have more of this resistance here, you're basically just giving more roads. Whereas in series, you've got a tunnel, and then a tunnel, and then a tunnel, and then a tunnel, and then a tunnel. And you know what that's like in Pittsburgh? It's a mess. You never stack tunnels on top like that. Here we're giving many different options for the drivers. So when we actually have parallel resistors together, the equivalent resistance will actually be less than the smallest resistor. Okay, that's the quick rule of thumb that you're doing this right. Your equivalent resistance has to be less than the smallest resistor. Furthermore, the way we actually get the number for this equivalent resistance is a little bit weird. It's actually going to be that 1 over the equivalent resistance is equal to the sum from 1 or I to however many you have of 1 over our resistors. And what we mean by that is if we were, adding, let's say like 1, 2, 3 resistors up, it would look like this. It would be 1 over R1 plus 1 over R2 plus 1 over R3. And you need to be super careful about that because this gives you 1 over the equivalent resistance. It doesn't give you the equivalent resistance. It gives you 1 over the equivalent resistance, which means that you need to take the reciprocal of that on your calculator real quick before you actually get an answer. So if we kind of think about this for a second, let's give these some values. We'll call this 1, we'll call this 2, we'll call this 3. We can't just say 1 plus 2 is 3 and 3 plus 3 is 6. This is 1 over 6. This equals 6. That doesn't make any sense because we've just violated our first rule. Our equivalent resistance has to be smaller than the smallest resistor. Our smallest resistor in our little example here is 1. So we better have a decimal as our answer here. Okay, so let's figure this out. Well, if we were to do this properly for this little example, where we've got just values of 1, 2, and 3, well, what's our common denominator here? Well, it looks like our common denominator is a 6. So that would be 6 over 6 plus 3 over 6 plus 2 over 6, right? And let's see, if I add all these together, that would give me 11 over 6, right? And this equals 1 over the equivalent resistance. So when I flip this, my actual answer here is going to be 6 over 11 as the equivalent resistance. Is this number less than 1? You betcha. Okay, so we need to be careful doing that. We need to take a final inverse, or rather a reciprocal of everything we do at the very end of this. So parallel resistors tend to give students a little bit of a hard time because you're not just adding things up like you are in series. You have to take this kind of strange looking summation here whenever you're adding them all together, and you need to do that flip out here at the end, and that is a very important flip move. If you miss that flip move, you're going to get the problem wrong. Okay, but remember, you can always check that by just saying, was the value I found smaller than the smallest resistor? Okay, and that will always be true. Even if you've got a resistance value of 1 here and a resistance value of 1,000, it will still be true. Okay, so with that, that's just how we kind of add up resistors right now. Later on in this circuits unit, we'll get into how to add some other things, like capacitors and inductors into these, and getting into Kirchhoff loops. But right now, this is where we're at. We're just adding things up. What we're going to see in our next few examples is how do we add up resistors for a circuit when we have a circuit with both series and parallel branches in it. So check out our next videos on how to do that. But for right now, this is finished. Take it easy. Adios.